Namaste everyone, welcome to our third class in mechanical properties of fluids. Today we will be discussing about one important property of fluids at rest, that's surface tension. But let's get this at the first instance that though we are dealing this property under mechanical properties of fluids, it is exhibited only by liquids and not gases. So the objectives are clear on your screen. We are going to discuss in very brief manner cohesive and adhesive forces, and in a detailed manner we are going to look at what is surface tension, and we are also going to look at some amazing examples that can be, some phenomena that can be explained on the basis of surface tension. Now let's look at what is force of cohesion. If molecules of the same substance are going to attract each other, that attractive force is what we call as cohesive force. And you all know that this is going to be maximum in solids, and that is the reason they have a rigid shape, a definite shape, but it is going to be least in gases. So if attraction between same molecules is cohesion, attraction between molecules of different substances is what we call as adhesion. But this adhesion, the adhesive force between two substances, is going to depend on the nature of the substances that are going to adhere to each other. Adhere is a common English word that means stick on to, you adhere to the rules of your school, you adhere to your promises. So adhering between two substances is going to be dependent on the nature of the substances. As for example, I have stated on my slide, gum has greater adhesive force for a solid surface in comparison to a water surface. Similarly, if you look at water, water wets glass. That means it has more adhesion towards glass, whereas water does not adhere to a lotus leaf. That means the cohesion between the water molecules is greater than the adhesion between the water molecules and the lotus leaf. Similarly, if you take the example of mercury, as much as water wets glass, mercury doesn't. That's because the cohesive forces between the molecules of mercury is much greater than the adhesive forces between mercury and glass. So adhesion is dependent on the nature of the substances that are exhibiting the forces between them. This is one simple pictorial representation of cohesion and adhesion. If you look at this picture over here, if I consider this as a liquid that is placed in a container, in the interior of the liquid, you can see cohesion, that is molecules of the liquid attracting each other. Whereas near the walls of the container, you can see that the liquid exhibits adhesive forces with the walls. Now, this is a simple representation, same molecules attracting each other, cohesion, different molecules attracting each other, adhesion. Now, this is a beautiful capture of dewdrops on leaf. So when rain falls down, it is the cohesive forces that is acting between the molecules of water that makes it form a droplet. But when it touches the blades of the grass, it is the adhesion between the water molecules and the leaf or the grass that makes it stick on to the leaf surface. Now, after seeing about cohesion and adhesion, how are we going to talk about surface tension? It is cohesion. It is the cohesive force between the molecules of water that is going to be the reason for the phenomenon or the concept of surface tension that is exhibited by fluids. So fluids, particularly liquids, the molecules of the liquids are also in random motion, even though the liquid might be at rest. So the random motion of these molecules, if you look at the surface, gives a very random boundary to the free surface because they are randomly arranged. We expect it because they are in constant motion. But if I am going to look at the interior of the liquid surface, you can see that every molecule is going to be attracted equally in all directions by the neighboring water molecules. They are going to be attracted in all directions. But if you look at the molecules at the surface, they are going to be attracted laterally and only in the downward direction, because they experience a very, very, very negligible force from the upper surface. This downward pull on the free surface of the liquid continues till the remaining water molecules are going to resist this attraction. And this leads to the surface molecules coming very close to each other than the interior molecules, forming a very smooth surface. And this smooth surface is going to behave like a skin, like a membrane, like a stretched membrane. Even if you look at a water droplet, all the molecules that are going to be on the surface are going to experience a pull in the inward direction, radially inward. They are going to be pulled towards the center, thereby forming a spherical structure. There is again a very beautiful capture over here of a water drop falling from a leaking tap. And you can see how beautifully the water drop forms a spherical shape. Now this is another zero gravity picture where the water drop actually forms a spherical shape. The water has a very high surface tension. Why? How are we going to answer the questions on the screen? I'm going to take you to chemistry. Now if you look at water molecule, a single oxygen atom is going to be linked to two hydrogen atoms. And what do we know about these atoms? Hydrogen is electropositive while oxygen is highly electronegative. So though they are bonded, they are going to carry a small positive charge over the hydrogen atoms and a small negative charge over the oxygen atoms. Now, due to the difference in the electronegativity and positivity of the oxygen and the hydrogen atoms respectively, there is going to be intermolecular attraction between the hydrogen and the oxygen atom. Intermolecular. Kindly understand, and this is what in chemistry we call as hydrogen bond. And this hydrogen bond between water molecules is the reason for the very strong attraction between water molecules, increasing the magnitude of cohesion between the water molecules. And that is the reason why these water molecules attract themselves more strongly. So this force of attraction that is going to pull down the water molecules at the free surface, and this force acting per unit length is what we are going to call as surface tension. This is another simple pictorial representation. You can see the interior molecules getting attracted in all directions, while the surface molecules, that is the free surface, gets attracted laterally. That's going to bring them closer to each other. That's going to pull them closer, more tightly on the surface than the interior, and downwards. So that means if you are going to consider a liquid contained in a vessel, they are going to, the free surface is going to behave like a stretched membrane. It's going to behave like a membrane, and any object that's going to be placed over it, it's going to stretch down, it's going to depress down to support the material. So how am I going to define surface tension? It's going to be defined as the property by virtue of which its free surface is going to behave like a stretched membrane under tension. Under tension, that's because it's going to be continuously pulled in the downward direction. And it tries to occupy as minimum area as possible, because it tries to come as close to each other as possible till the repulsive forces are going to push them. You have also studied this in chemistry and in physics, where the molecules, intermolecular forces, are both attractive and repulsive. The more closer you try to come, the more repulsive it becomes. So it tries to come so close as possible till the repulsive force comes into picture. So it tries to occupy as minimum an area as possible. And this tension is what we call as surface tension. Now, these are some other beautiful captures of the stretched membrane behavior of liquid surface when objects are going to be placed over it. You can see a needle, a steel needle whose density is much greater than the density of water, a steel paper clip, again the density greater than that of water, placed on the surface of water, and you can see how the water surface is supporting them. You can see the depression that these objects are forming on the liquid surface, giving you a proof that the free surface is behaving like a stretched membrane. And you can see here, these are insects that we call as water striders, and their feet, when they rest on the water surface, you can see in the picture attached over here, wherever the feet of these striders are touching the water surface, you see a very small depression. Wherever their antennae are touching, you see a small depression. The water bends down, the water stretches, the water paves way for them to balance themselves on the liquid surface. And this again is because of the phenomenon of the force acting per unit length, that is surface tension. Now, these are some of the examples again, which I'm going to show in the form of video picked up from YouTube, showing these phenomenon of surface tension in some of the examples. You can see this paintbrush, dry paintbrush, the bristles which are all spread out, and when it is inside the liquid, you can see that the bristles spread apart. But see what happens when it comes out. All the bristles cling to each other. That's because the surface, the water at their surface try to occupy minimum area, try to attract each other due to the cohesion between them, and try to come closer to each other, bringing the bristles closer to to each other. That's why the bristles of the paintbrush actually cling to each other when we are going to pull it out of the liquid medium. Now, this is another example which I want you to look at. All these examples you can try on your own using simple things that are available in your house, and do capture those videos and share with me if you are so interested. And let's look at this. You can see a rectangular or a square frame they have formed using nothing but drinking straws, and they have dipped it in a liquid made of dishwashing liquid. You can see a beautiful soap film formed there, and they have put an irregular loop that is formed using a normal sewing thread. But what happens when the loop is punctured? You can see that immediately the irregular loop forms a regular circle. And this is because when the loop is punctured, before the loop was punctured, there is a force acting, balanced forces acting on any region of the liquid, the soap film layer. But the moment it is punctured, one part of the balanced force is cancelled off. So the forces that are acting outside the loop are pulling it, are stretching it to the maximum, forming a circular loop that was initially of an irregular shape. Another example to show that the liquid surface is pulling apart. They are pulling each other in towards each other because of the cohesive forces. Now, another example over here, which cannot be actually done at home. The previous two examples that I showed, you can still try it at home, but this one is a little difficult because you need to maintain the density. What you are actually seeing here is a container having water and alcohol mixed in such a proportion that the density becomes equal to that of the density of olive oil. And what they have done over here is they have actually used a pipette to add a few drops of olive oil inside this mixture of water and alcohol, and they have coalesced them together to form a single oil drop. And you can see here what has happened. The oil drop is suspended in a perfect spherical shape. Now, this is actually called as an anti-gravity experiment, Plateau experiment. Now, why is this anti-gravity, or what happens to the gravity that is acting on the olive oil drop? The density is so maintained that the weight of the oil drop is exactly balanced by the buoyant force. So gravity cancels out and the oil drop suspends in the spherical shape. Why spherical? We have already explained using surface tension. And this experiment proves this, that what we have been talking about so long. Another thing that I would like you to watch, and there's again a video that is taken from YouTube. Sorry, let me go back to this. So you can see that there are so many droplets that they have pipetted out, and they are coalescing it into a single oil drop. Now, this single oil drop, which is suspended, if it is going to be disturbed, see what's going to happen, how beautifully it remains suspended, defying gravity. And when this oil drop is going to be disturbed, see what happens. It forms a beautiful ring. Keep watching. It is going to be disturbed once again. Once it settles down, you can see the formation of a wonderful ring. And that ring comes back again because the molecules are pulling out. You're trying to push them apart. You're trying to push them apart, but they don't stay apart because their cohesion is greater. Surface tension pulls them. The surface molecules are pulled closer. And the more you try to pull them, push them apart, they try to come closer to each other at every point of time, maintaining the spherical shape. You can see over here, again, they are trying to disturb it. Again, they are trying to push it apart, and these molecules come closer to each other. Some wonderful examples of surface tension. Now, how am I going to measure surface tension? If I'm going to consider an imaginary line drawn on a liquid surface, as I told you during the soap film experiment that you viewed, there are forces that are acting on either side of any imaginary line that you consider on the surface that are going to pull apart that particular point, the molecules on that line on either side equally. So let us consider the force that is acting on one of the side to be F. So that means the opposite side is also going to be F. Let me consider the length of this element that I'm going to consider, the imaginary line, as L. Now, for a given liquid at a given temperature, this force that is acting, which is tangential to the surface and perpendicular to the line element under consideration, is always directly proportional to the length of the line element that is taken into consideration. I repeat, the force that is acting tangential to the surface, because it pulls tangentially out. You saw it again in that experiment of soap film. It pulls out tangential to the surface and perpendicular to the line element, right? Perpendicular to the line element. Then F is proportional to L. So F by L is a constant for a given liquid at a given temperature. And this constant is what we are going to call as surface tension T. So T is going to be equal to F by L. Is that clear, children? Now, if I'm going to put this in words and define it as to what is surface tension, now how am I going to define surface tension? Is measured as the force acting per unit length of an imaginary line drawn on a liquid surface. Now, why have I highlighted a liquid surface? Please understand, if there are multiple liquid surfaces, this will increase because it is per surface. On a liquid surface, the direction of the force being perpendicular to that particular imaginary line and tangential to the liquid surface. Now, how am I going to find the dimension? We know T is equal to F by L. Now, what are the dimensions of F and L? It's going to be mlt per minus 2, and that of length is L. So if I'm going to cancel out the L, then what do I have for the dimensions? The dimensions is going to be simply mt per minus 2. You have done dimensions in the part of Mrs. Chandrasekhar, so that will be mt per minus 2. Now, apart from surface tension, we are going to look at something called surface energy. Why are we going to discuss about surface energy? Now, the moment you punctured the loop became a perfect circle. The molecules were pulled apart. Now, what had to be done in order to pull them apart? Because the molecules were actually attracting each other on either directions of the imaginary line, but you made them to pull out in a different direction. So if you want to stretch, if you want to increase the surface area, because we saw that they try to occupy the least surface area. So if you want to stretch a liquid surface, you need to do so against the attractive forces that are trying to occupy minimum area. So anything you need to do against an attractive force, you need to do work. So work has to be done in order to stretch a liquid surface. That work done in order to stretch a liquid surface is going to be stored on the free surface of any liquid in the form of potential energy. And that potential energy is what we are going to call as surface energy. So let us assume that the soap film that you formed using your straw, one of the straw is movable, one side of that particular rectangular frame is movable, and let us assume the length of that rectangular frame is L. And suppose you pull it out through a distance X by applying a force F. You know that tension is acting in this particular direction, so you have to apply a force. Suppose if I'm going to apply a force F to pull it out, then what do we know? We know tension is equal to force per unit area. So this tension that is going to be acting will be F by, if I consider the length as L, F by, if you had said L, please pause the video, pause the video and pause yourself for a moment and think, can I put L? Is it this tension on the soap film, is it acting on only one surface? No, because when I consider a free liquid surface, there is only one free surface that is exposed to air. Whereas if I'm going to consider a liquid film please, it has two surfaces, upper surface and lower surface. And I told you surface tension is per surface, a liquid surface, and I have two surfaces over here. So the length doubles over which the surface tension acts. So the force that I have to apply has to be equal to T times 2L. Now, if this is the force and the displacement that I have produced is L, what am I going to say about my work done? It's going to be T times 2L times X. Now, this is the work done in order to pull it out. Now, this work done is going to be stored in the form of energy on the surface. But this work done per area of increase. Now, this is going to be the work done. Work done is going to be T times 2Lx. If this is going to be calculated per unit increase in area. Now, how much has this area increased? Again, twice L times X, the area has increased. Now, if I'm going to cancel out the common terms in the numerator and the denominator, I am left out with nothing but surface tension. And this quantity of work done per unit increase in the surface area is what we call as sigma, the surface energy of the free surface of any liquid. So what have we arrived at? We have arrived at the surface energy being numerically equal to the surface tension. So sigma becomes equal to T. Numerically equal, please, because surface tension is force acting per unit length. Now that I have proved this, I can also say it is the work done per unit increase in surface area when a liquid surface or a stretched surface is going to be further pulled out to increase its surface area. But please understand that this is constant for a given liquid at a given temperature, because temperature differences cause further differences in your surface tension. So sigma is going to be equal to T. The work done per unit area in increasing the surface area of a liquid is what we call as surface energy. So tension can either be measured as Newton per meter because it is F by L, or it can be measured as joule per meter square because it is work done per unit increase in area. That's surface energy. So you've seen the relationship between surface energy and surface tension too. So that brings us to the end of our lesson, and I hope we would have achieved these outcomes. We tried to define adhesive and cohesive forces, and we have seen the relationship between surface energy and surface tension. And there have been certain examples that we tried to explain on the basis of surface tension. Now, what I would like you to try and do is try and capture some beautiful pictures showing the stretched nature of liquid surfaces. Try and do some simple experiments. You also have the pepper grains with the dishwashing liquid, the pepper grains being thrown out of the liquid surface. You have milk with food color and a dishwashing liquid, where the food colors form some beautiful patterns when touched with dishwashing liquid, so on and so forth. Internet has so many other examples where you can actually describe surface tension using some simple things available at home. I would like you all to try experiments on your own and do share the video with me, and keep studying as we will be moving on to some more interesting topics in this lesson. And at all times, stay safe.